If something is staring you in the face, why would you look somewhere else for an answer? Because believe me, the answer is staring you in the face right now. And what it is the consecutive odd numbers and what happens immediately after those consecutive odd numbers that tells you everything you need to know. And unfortunately, if you've got a series of numbers that include the even numbers, you're not going to see everything you need to know to solve the conjecture. So I'm going to make the claim that I have solved the conjecture, and I won't prove that, or I won't prove my proof in this presentation, possibly in the next one. So here we see that the second column after the consecutive odd numbers, and by the way, it really helps to put all the odd numbers, all the sequences together. When I first learned about the conjecture 4 years ago, the very first thing I did was write the code in Excel, which is the easiest way to do it, to generate about 1,000,000 sequences. Turns out I only needed about 100 sequences to see what was going on very, very clearly. And what that is, obviously on the second column, we have the operation operating on every odd number in the number line. And, that's the one we know, 3x plus 1. So in each case, we get an even result. 11 times 3, 33, plus 1, 34, and so on. I don't care about that because that's just noise. That's just there to entertain mathematicians. It's noise. What I care about is the next odd number, because don't forget, 1 is an odd number, and that's really the number we care about most. So the even numbers are just intermediate transitions that are not required. You can go straight to the next odd number if you know what the ratio is between the odd numbers. So that's what I'm going to talk about. So there are actually only 3 operations. And we can see approximately what they are. Well, we can see very clearly that 25 to 19 is going to be about 3/4. 19 is 3/4 of 25. We're going to see, but it's not exactly that. And again, that's another thing that might trip up mathematicians who call themselves number theorists, because in number theory, whole numbers are the name of the game. We're not interested in fractions of numbers. If we see fractions of numbers instead of whole numbers, that just is a red flag right there that we're not doing things right. And so, if you know something like Fermat's last theorem, or anything to do with prime numbers, or the twin prime conjecture, or the Goldbach's conjecture, we are interested in whole numbers. Now, if the Collatz conjecture is in the field of number theory, which is possibly not the case, but we are, in fact, dealing with whole numbers. We need a whole number solution because we end on 1. I'm just saying it might not even qualify as number theory. It could just qualify as arithmetic, in which case there's a level confusion the mathematicians have because they have all these amazing tools, but they don't actually need to use them in this particular conjecture. See, they don't even question that possibility. They have these tools, therefore they must be used. The Collatz conjecture has not been proven in 80 years, so therefore maybe our tools are not powerful enough. But as a famous mathematician stated, and God help me, I can't even think of his name at the moment, poor Erzos, he said maybe mathematics is not ready for the Collatz conjecture. Now, it's possible he was joking. It is indeed possible that he was joking. Or he had level confusion. Either one. I suspect the tools are too powerful for this conjecture. This conjecture is essentially a childish conjecture, and you get that from the way it's expressed usually, which I never repeat. That's a giveaway right there, in my opinion. And I saw through it within a couple of weeks of learning of a conjecture, but I do not wish to sound arrogant about it. So we can see approximately 19 is 0.75 of 25, and 47 is 1.5 of 31. And this other mysterious one is way off a whole number. Well, of course, 1.5 isn't a whole number either, but you can express that as 3 over 2, which might satisfy a number theorist. And of course, there's this whole field of number theory called complex analysis, which just goes off in the direction that would never originally have been conceived of by mathematicians a couple of hundred years ago, and that's imaginary or complex numbers. No, totally unrelated to this conversation. I'm just going off on a tangent. But this one, 7 to 37, is a very odd ratio. Indeed, it's less than 0.2. It's precisely 0.189. So what's going on here? What are we going to do about this? But we're going to see these ratios repeating themselves, the first two over and over again. This third one, depending on how many even divisions there are. So that ratio is actually determined by how many even divisions there are, and that's perfectly what you would expect if you think about it, because we're doing division by 2 of even numbers is all the way until we hit an odd number, and in the case of powers of 2, that odd number is 1. So I think there's an example here. 21 after multiplication by 3 and addition by 1 is 64, and then the division goes right all the way down all the way down to 1, which is just the next one off of this area of the table. So let's press on. Oh, that was meant to pop up earlier. That's just covering that silly column of even numbers. The one of it is the result of 3x plus 1, which I don't give a damn about. And I'll try to justify that, but possibly not in this presentation. I think the rest of this presentation is going to be very fast. There's just a few more slides to show. I just wanted to emphasize the predictable pattern or structure when you see all the consecutive sequences together. And so I was talking about 1.5, an approximation, and we'll get to precision in the last slide. So you see that every other odd integer has the property of multiplication by 1.5, and that's what makes the sequence, that's what makes the Collatz conjecture interesting. The numbers go up quite a bit before they go down, and you know, the question is, if they go up once, why don't they go up again and again and again forever? Won't get into that in this one, maybe the next one. So yeah, we see 11 goes to 17, 15 goes to 23, 19 goes to 29. If you do these ratios, they're all going to be, I think, very, very close to 1.5, but I don't care about that because I can get to a perfect precision 1.5. So now we go to the next one. And here we see, if we go one step further to the right, one step closer to 1, we have this 0.75 operation going on. So, yeah, so this is a huge clue to why the conjecture is extremely solvable, because notice that you go 2 steps further to get to 0.75, whereas you only go 1 step to get to 1.5. Surprising. I wonder why. Let's move along. Here I've also highlighted these numbers, which actually we're going to eradicate. Now these numbers seem to be about a third of the original integer odd number, They seem to be about a third, and I don't care about these either. Notice there are 3 even numbers mediating these. When we get to my proof in the next presentation, I will show you why you don't need to worry about these. You also have something like this, or what appears to be a real outlier. You know, what proportion this is, I don't know. It's less than, somewhere between 4 and 5, or it's actually 5/5, and a little bit extra, but not useful to me at all. And I will show you how to get rid of these, or not how to get rid of these, but because I want to emphasize something, because I've probably already misspoken on this. Every odd number in conventional sequences a part of the way I express sequences too. I have some extra numbers. So that makes my method of generating sequences a proper superset. My sequences are always a proper superset of the conventional sequences of the odd numbers, a proper superset of the odd numbers. I eliminate the even ones. And I also don't really think of them as sequences. I think of them as atomic input-output operations. But that's not what I'm getting into in this brief presentation. Here, I have just further filled in some more things. Okay, I filled in the even numbers in gray, which I already did that. And I also got the powers of 2 here, which I also spoke about already. So these are all like different features you will find when you look at sequences, and they're staring you in the face and you're staring at them, and you don't go in some crazy tangent of number theory, because you don't need to do that. Let's start with the basics. Let's begin with the obvious stuff. And maybe we don't even need to go to the arcane and complex stuff. Like I always think about that huge paper that Terence Tao, the most famous mathematician in the world, wrote 3 or 4 years ago, in which he had to put in the title the qualification almost, not once, but twice. Almost, I call it the almost paper. And, you know, he was using Diophantine equations. God knows what he was doing. It's just drivel as far as I'm concerned. Yeah, I'm really in an irritable mood today, and that's because I had a bad experience this week with quite an important number site, and I better not get into the details or I'll get into trouble. But it ended very well, and I was honored and privileged to email with the founder of this site, who's an incredible man. I think he's in his 80s now, and a fellow Brit. I don't know if you noticed, I do have the remnants of a British accent. And he was just very, very kind to me. He didn't make me feel bad. And yeah, but I'm still a little bit irritable about it. So this corresponds beautifully with the 3 congruence operations that I have previously spoke about, and I'll just recap in the last slide. So this first one is operation A, which is 1.5. The ratio B is B is ratio of 0.75. Actually, I cheated when I put C there. I shouldn't have even put it there, because it's actually it's hidden and it's over a column, and 7 has got nothing to do with it. But as I said, the 7 is still there. It actually follows the operation C. I put a question mark there, but we know what happens there. Next digit is 1. Okay, so actually this is the last slide, but this is a really important bit, because I am showing you how to get a whole number here. So if you make n an even number and multiply by 1.5 and subtract 1, you get a whole number. And this is not a trick, this is just really, really works. You will see this in the A and B operations do exist in the conventional sequences. You will get exactly the same odd numbers. So B, again, you get, in this case, we subtract 1 from the odd number, and then we multiply by 0.75, and then we add that one number back again. Again, we get a perfect integer, a whole number, a positive integer, and we're good. The third case, and I think I must have just stumbled upon this by accident, because the first intuition is, oh, you've got to divide by 3. You've got to undo the 3 plus 1 operation. That's not what I did. I stumbled upon this, and I was looking back at my old posts on Quora, trying to get to the bottom of why I discovered this, and I did see the mental process I was going through. So it wasn't a total accident, but it works out beautifully, because these are the hidden numbers, but in the odd sequences, they're always followed by a number from the even odd sequence. So these are superset numbers, and it doesn't matter. It works out beautifully. Actually, they're extremely important in my proof. So it's m minus 1 multiplied by a quarter. And as I say, this is a superset number hidden in the even odd sequences, but it's also a convergence number. And it turns out that every integer, including 1, has this convergence integer. So, and it's hidden. And I'll just, I'm not very good with examples, but I do remember that 5 is the smallest case of a C operation, so minus 1 divided by 4, and you get 1. Now you get this with every single number. It's just hidden in the even odd sequences. I don't know a better way to do it, to say it. It's just disguised by 3 divisions of 2. So when you see 3 even numbers in succession, you know that there's a congruence of a convergence of 0.25. It's n minus 1 times 0.25. And looking at this, it's not just those cases where it's 3 even ones. Those are the, for some reason, that's what I'm thinking of now, but it's actually every single case. And it disguises a lot of interesting things. For example, 27 is usually considered that's the only place you see 27 is at the beginning of a sequence. I don't look at it that way at all. And I think it's highly provable that 109 is the next or the previous step in the sequence. And in fact, 27 is the smallest number in this very large series of numbers that goes on to infinity. But the next larger one is 27. No, the next larger one is 109 minus 1, 108 divided by 4, 27. But when you come back that way, it skips 27. It skips 27 in the even odd sequences, and that's why no one knows about it. No one realizes that 27 is the smallest step in a series of numbers, and that 109 is the next biggest one. But if you look at the succeeding numbers in the sequences for 109 and 27, I think they both continue with 41. That's exactly the way convergence works, and that is beautifully hidden. And my proof rests upon the fact that every odd number belongs to an odd sequence. And we also know that if the Collatz conjecture, if the convergence to 1 is true for the odd numbers, that means it's also true for the even numbers. This is accepted. And this is accepted by mathematicians. There's no controversy about that. So if we can prove that every odd number is included in a sequence, then the game is over. The jig is up for the conjecture, and it's a beautiful example of the pigeonhole principle, except it's so extreme. It's such an extreme example of the pigeonhole principle that it's almost laughable. It's almost, yeah, it's a joke. It's a cosmic joke. it's a beautiful, beautiful example of the universe working the way the universe must work. And on that point, I will say good night. Bye-bye.